Hello students, welcome to EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about mapping, homomorphism and isomorphism in this module. This is from paper Mathematical Physics. So students, let us see what we are going to learn in this module. In this module, you will get to know how seemingly different groups are related to each other through a mathematical link which is called the mapping between two groups. You will learn one of the most important results in group theory, namely permutation symmetry group contains all the other groups as subgroups. There may be correspondence between the elements of two groups. Consider two groups G and G prime. The elements of G are G1, G2 and so on, and the elements of the group G prime are G1 prime, G2 prime and so on. Now, we consider a mapping F from the group G to the group G prime. What does this mapping means? It means that we assign to each element G of the group G an element G prime written as f of G, which is an element in the group G prime, such that for every G prime belonging to G prime, it is the image of at least one of the element G which belongs to the group capital G. This correspondence or mapping between the elements of two groups G to G prime can be 1 to 1 or many to 1, which means to each element of the group G, there is a map which takes to only one element to the group G prime. Or it could be that two elements which are different in the group G are mapped to the same element in the group G prime. If this mapping preserves the group multiplication, that is, if the elements in the group G satisfy the multiplication rule G1, G2 is equal to G3. So, and the mapping F takes us from the element G1 to G1 prime, G2 to G2 prime and so on, then it should imply that G1 prime, G2 prime is equal to G3 prime. What it means that the multiplication law which is obeyed by the elements of the group G after the mapping of elements from group G to G prime, the mapped elements in the group G prime should also follow the same multiplication law, that is f of G1 into f of G2 is f of G1 G2 for all elements G1 and G2 which belong to the group G. Now, if the mapping F is 1 to 1, as we discussed, that is if one and only one element of the group G prime is an image of an element in the group F, then it is an isomorphic or a faithful mapping of G or G prime. The two groups are said to be isomorphic to each other and have the same structure. So, if there is 1-to-1 group, 1-to-1 mapping from a group G to the group G prime, and if the same multiplication law holds for the image as is obeyed by the elements in the group G, then the two groups are said to be isomorphic. It's easy to see that the identity map F is equal to ID, which maps every element of G into the same element, that is, the identity map maps an element of G to itself for all G belonging to the group G identity map always exists and is isomorphic. We will now discuss some examples of mapping, and mapping which is homomorphic and isomorphic. To begin, suppose every element of the group G, that is G1, G2, etc., are mapped to the group G prime, whose only element is the identity, then this is an example of a trivial homomorphism. An example of isomorphism is that if you consider a group G of rotations which has 4 elements, E, C4, C4 square and C4 cube, where C4 is a rotation about an axis by an angle pi by 2, C4 square is a rotation about pi, and C4 cube is a rotation about 3 pi by 2. And if G prime is a finite group of numbers which are 1, I, minus 1 and minus I. Now if we consider the mapping, that identity in the group G is mapped to the number E of the group G prime. The rotation C4 is mapped to the element I of G prime, and C4 square is mapped to minus 1, and C4 cube is mapped to the element minus I of the group G prime. Now it's very easy to see that this group preserves the group multiplication. For example, in the group G, C4 cube is equal to E. Whereas after mapping, when C4 is mapped to I and C4 cube is mapped to minus I, then we have minus I into I is equal to 1 in G, or C4 cube, that means C4 multiplication rule is preserved. Likewise, C4 square, C4 cube is equal to C4 in G, whereas in G prime, we have C4 square corresponding, a mapping of C4 square is minus 1 and of C4 cube is minus I. Therefore, C4 square, C4 cube goes to minus 1 into minus I is equal to 1, which is in G prime. Thus, the two groups are isomorphic. I will discuss now another example. We consider a symmetric group D, which is the group of symmetry operations on a regular triangle, and we will show that the symmetric group D3 is isomorphic to the permutation group or the symmetric group of 3 elements S3. Let us first look at the symmetry operations of a regular triangle. So we consider XYZ to a regular triangle. It's obviously that is a symmetry operation, is an identity operation which does nothing to the triangle. The another operation is C3, that is a rotation of 120 degrees in the plane of the triangle. Suppose I consider an axis passing through the center of the triangle and rotated by 120 degrees because of the fact that the triangle is a regular triangle. After rotation, the triangle maintains the shape. C3 is a symmetry of the triangle. Likewise, I could rotate by an angle of 240 degrees, which also is a symmetry. So C3 square is another symmetry of the triangle. Then suppose I consider the axis ZZ prime and rotate it by 180 degrees. Rotate along this axis by 180 degrees, which will change x to y and y to x. Then obviously this is a symmetry. This symmetry can also be seen as a mirror symmetry. If we put a mirror normal to the plane of the triangle coinciding with the line ZZ prime, then after reflection x goes to y and y goes to x. So this is a symmetry. This symmetry, a rotational symmetry, all the mirror symmetry, we represent by sigma nu z, which is rotation by 180 degrees about ZZ prime. Likewise, a rotation by 180 degrees about XX prime is a symmetry which we designate as sigma nu x, and similarly sigma nu y. So the group D3 has 6 elements. The multiplication table for the group D3 has 6 elements. One being the identity, second the rotation by 120 degrees in the plane of the triangle, which is C3, rotation by 250 degrees, C3 square, rotation by 180 degrees about ZZ prime, sigma nu Z, rotation about 80 degrees about XX prime, sigma nu X, and sigma nu Y, a rotation by 180 degrees about YY prime. The multiplication table of the group D3, which has elements now E, C3, C3 square, sigma nu Z, sigma nu X, and sigma nu Y, can be easily constructed by noting, for example, consider on the triangle, apply the symmetry operation C3, which is a rotation of 120 degrees in the plane of the triangle. This takes the vertex X to Z, Z to Y, and Y to X as shown here. And then when we rotate by 180 degrees about the axis ZZ prime, then Y X are interchanged, and we are back to the triangle with which we started, which shows that C3 sigma nu Z takes the triangle XZY to the triangle ZXY, which can be achieved by a single operation wherein we reflect or rotate about an axis passing through YY prime by an amount equal to 180 degrees. We continued, and the multiplication table then we obtain is shown in the slide. Now let us look at the multiplication table of the symmetry group S3, which we have discussed earlier. It has 6 elements given by as E, A, B, C, D, and F. The multiplication table of the symmetry group S3, as discussed in earlier modules, is reproduced here. And when we compare this multiplication table of the group S3, the symmetry group, with the multiplication table which we derived before it for the rotation of the triangle, and if we make the correspondence or the map whereby the identity element of the permutation group is mapped to the identity element of the group D3, the element A of the symmetry group is mapped to the rotation element C3, the element B of symmetry group is mapped to C3 square, that's a rotation by 240 degrees. The element C of the symmetry group is mapped to a rotation about the ZZ prime by 180 degrees, that is sigma nu Z. The element D is mapped to sigma nu X, and the element E is mapped to sigma nu Y of the group D3. These two groups with this mapping can be easily seen to be isomorphic to each other, because there is one-to-one correspondence between the elements of the symmetry group with the rotation group D3, such that the group multiplication is preserved, and therefore the two groups are isomorphic to each other. Also note that the subgroups are the groups constituted by 3 elements EAB and 2 elements ED, another subgroup having 2 elements EC, and yet another subgroup having 2 elements EF. We now define the concepts of domain, codomain, and the kernel in the context of mapping. Suppose we have two groups, G prime and G, and both the groups are of real numbers, that G is a group of real number R and G prime is also a group of real number R, and if X is an element of R, which means X is a real number, then if we consider the mapping F, form the group G to G prime, which takes an element in the group Gx to square of itself for all elements X belonging to the real number set. In familiar language, the map takes X to X square and is written as f of X is equal to X square. G and G prime obviously are different groups, even though they are equal to R. Why? Because for any x belonging to G, since x square, which is the image of x by this mapping, greater than 0, which means that fx maps elements of G into positive definite part of G, plus the 0, of course. In addition, the elements x and minus x both are mapped to the same point, x square, in G prime. This is an example of 2-to-1 mapping. Now, the set of inputs in G, that is the real numbers, x. This is called the domain of the map. And the set where the mapping takes it, they live in the group G prime. So that is, the output is in G prime. Where the output lives, that region is called the codomain. So domain F and codomain F are the regions where domain F consists of all the elements in the group G which are mapped to the group G prime, and all of those images live in the codomain F. Having defined the domain and codomains for mapping from one group to the other group, we will now discuss the equality of the maps. Suppose we have two maps, F and G. We say they are equal and we write F is equal to G if and only if domain of F is equal to domain of G and codomain F is equal to codomain G. For all x belonging to the domain F, f of x is equal to gx. What do these conditions tell us? These conditions tell us that domain and codomains must be the same, while the third condition ensures that both f and g maps to the same point in the codomain. We say that because we have said earlier that f of x is equal to gx. So, which means that both f and g maps to the same point in the codomain. Note that the map fx is equal to x and gx is equal to x may look the same. But if domain of f is z, which is a set of complex numbers, while domain of f is capital R, which is the domain of real numbers, then obviously the map f is not equal to the map G. Consider now a map fx is equal to x square, which means that for every element x in the map G, we assign an element x square in the group G prime. So there exist points then in codomain F that has no partner in domain F. For example, no points are mapped to negative values. A map which maps to the entire codomain, that is, if image of F is the codomain of F, this is called an onto map. Obviously, the map that gives different outputs to different inputs, that is a map F from G to G prime, such that for G1 and G2 elements belonging to the group G, and if the element G1 is not equal to the element G2, then f of G1, that is, f of G1 is map of G1 that is not equal to f of G2. Such a map is 1-to-1. Suppose G1 and G2 are groups. Then the homomorphism F says G1 going to G2 maps more than one element of G1 into G2. That is, we are considering a homomorphism wherein more than one element of G1 is mapped to G2. Since the map is not necessarily onto, the images of F is only a subset of G2. That is, image of F is a subset, not a subgroup, a subset of G2. In addition, the set G1, which is mapped to the identity element E2, which belongs to the group G2, is called the kernel. That means all those elements of the group G1 which are mapped to the identity element of G2 is called the kernel. So kernel consists of all those elements in the group G1 which are mapped to the identity element of the group G2. So kernel of F is defined as those elements G belonging to G prime such that F of G is equal to E2, the identity of the group G2. Thus, the kernel forms a normal subgroup of G. We will now rephrase what we said earlier with the help of a figure shown in the slide. Consider a homomorphism F maps the group G1 to the group G2. The domain of G1 is mapped to the codomain in G2. By definition, the kernel of G1 is mapped to the identity of G2. The entire group G1 is mapped to a subset of G2. If it so happens that the map F maps to the entirety of G2, that is, all the points in the group G2 are the image of some elements in the group G1, and if the kernel of F is trivial, then the map F is said to be isomorphic. We will now prove certain assertions. Number 1. Identity of G1 has to be mapped to the identity of G2. Suppose G1, E1 belongs to the group G1, so that the map of G1, E1 is equal to F of G1 into F of E1. That is, the image of G1, E1 is the image of G1 multiplied by the image of E1. But the image of or F of G1, E1 is equal to F of G1 because G1, E1 is equal to G1. Hence, F of G1 is equal to F of G1 into F of E2, which means that F of E1 is equal to E2. That is, the identity of G1 is mapped to the identity of G2. Likewise, inverse of G1, G1 prime, is mapped to the inverse in G2. Let G1 prime be the inverse of G1. Then the map F G1, G1 prime is equal to map of G1 into map of G1 prime is equal to the map of E1, which is E2. Therefore, what does it mean? F of G1, G1 prime is equal to F of G1 into F of G1 prime is equal to F of E1, which is equal to E2. Thus, F of G1 prime must be F of G1. Or F of G1 must be F inverse of G1, that is inverse of F of G1. We will now prove what we said earlier, that the kernel F forms a normal subgroup of the group G. The proof goes as follows. We first need to show that the kernel F forms a subgroup. Then we would show that subgroup is indeed a normal subgroup. Since kernel F is a subset of the group G, we first show that it obeys the group laws. Let the set K consist of all the elements of kernel of F. Number 1. If it has to form a subgroup, it must obey all the group laws. So that means the identity should exist. So it must possess identity E1 of G1. Since F maps to the identity of G2, closure property should be satisfied. If the elements K1, K2 belong to K, then by the definition of homomorphism, F of K1 into F of K2 is equal to F of K1, K2, which is equal to E1, E2, which is equal to E2. Hence, K1, K2 also belong to K. Inverse, existence of inverse. If element K belongs to subset K, then F of K inverse is equal to F of K, K inverse is equal to F of E1 is equal to E2. Thus, K inverse is equal to K. Finally, the associativity. Since G1 is a group, K inherits the associative property, and therefore the associativity is automatically satisfied. So we have proved that the kernel forms a subgroup. In order to prove that the kernel of F forms a normal subgroup, we had to show that for every K belonging to capital K, for any element of G which is an element in the group G, if G, K, G prime must belong to K. If we can prove this, then we have proved that the kernel forms a normal subgroup. Using the defining property of a homomorphism, map of f of G, K, G prime is f of gk into f of g prime is equal to f of g into f of k into f of g prime is equal to f of g. F of k is the image of k, which is E2, and then we have f g prime, f of g1 prime, which is nothing but E2. Hence, gkg prime belongs to k for all elements G belonging to the group G. This completes the proof. We now will discuss Cayley's theorem. It's one of the most important theorems in group theory. The proof of Cayley's theorem is quite involved and may be left in the first reading. So what we will do to state the theorem and just indicate how the proof goes without going through the complete proof. Cayley's theorem is important because it says that any group G is isomorphic to a subgroup of a permutation symmetry group. So any group which you can conceive is a subgroup of the symmetry group, which is a permutation group, in the sense that all other groups are subgroups of the permutation group S. The proof will not be given, but to prove it, we have to now establish certain things, which are the following. Consider the group G, whose elements are G1, G2, etc., which belong to the group G, and it has the group multiplication law, Gij is equal to Gk, which belong to G. We now consider a one-to-one map F, which maps this group G to the symmetry group X, such that group multiplication of G is preserved. That is, the mapping is homomorphic. So we consider a homomorphic mapping of the group G to a group of symmetry S, group of permutations, such that Fg1 G2 is equal to Fg1 into Fg2. So we now need to establish that f of G1 into f of G2 results into an element of the permutation group S for some S. For a given set G is equal to G1, G2, etc., the set of all images f of G1, f of G2, f of Gn forms a group under the group multiplication law of the permutation group. If these requirements are fulfilled, then the map is an isomorphism and is a subset of the permutation group S itself is a group. So, students, we are now in a position to summarize what we have learned in this module. Number one, group homomorphism are maps that preserve the group multiplication law. These maps could be one-to-one or many-to-one. The identity map always exists and is isomorphic because the identity map takes any element in the group G to the same element in the group G prime. The identity and the inverse elements of two groups G1 and G2 are mapped to the identity and inverse elements of each other. And most importantly, about the permutation of symmetry group, the result which we have discussed, though not quite proved, is that the permutation of the symmetry group contains all other groups as a subgroup. Is one of the most powerful results in group theory. Thank you.